Just like to thank everybody for joining us today. We're going to be talking about GPU accelerated radiative view factor calculations and their applications and implications in headlamp design and thermal analysis. So I'm joined today by two of my collaborators, Harold McFarland and Robert Harpy at Stanley Electric, and I'm Martin Kenward, part of the Maya HTT organization. So the talk today is split into two parts. I'll begin with setting the scene for what my colleagues will be talking about, specifically how we've managed to accelerate thermal analysis in headlamp design cycles. And the first part of the talk is lighting up the future of headlamp design with GPUs. And so if people don't know much about Maya HTT, we're an organization which has been partnered with Siemens for quite a long time. We have our roots in space systems thermal analysis with over 35 years of simulation technology behind us. In 2021, we were a North American Partner Award winner in Siemens Digital Industry Softwares. We have a long history of consultancy and integration into SimCenter 3D products. We've authored over 30 plus modules for Siemens. 75% of our staff and scientists are scientists or engineers. And we have our hands in the whole gamut of CAE, CAD, including product lifecycle management, design, simulation, manufacturing, IoT, custom software development, automation, and optimization. And if you don't know much about Maya HTT, but you'd like to find out more, I encourage you to visit the Maya website and find out a little bit more about us. So to begin with, I'm going to set the scene for what the crux of the talk is today and how we've used GPU computing technology to expedite thermal radiation calculations in SimCenter 3D thermal flow. So what we're talking about here today can be found in the SimCenter 3D thermal flow suite of products. And what we're going to be focusing on is how, or rather what we've done to accelerate calculations which are very time consuming in thermal analysis, specifically related to headlamp thermal analysis. Thermal radiation is really an artifact of electromagnetic radiation being incident upon any object, whether it's a headlamp or whether it's you standing out in the sun on a nice summer day, warming up, or a Mars rover on the surface of Mars. So you can imagine in a headlamp, you have a number of lighting components, and those lighting components produce electromagnetic radiation, which is then, reflected and refracted and bounced around inside a headlamp, thus heating up all of the constituent components, including the LEDs and circuitry and materials itself. So thermal radiation really is a complex phenomenon, and it's very difficult and computationally expensive to model. It's a function of the temperature of the components themselves, the geometry, the environment, the materials. And as we'll show, what we're aiming to do is really expedite this part of the simulation process for our thermal analysts. So there's many methods that exist. We're not reinventing necessarily a new method. We're implementing an advanced functionality on GPUs to expedite these calculations. And specifically, we were focusing on helping out our headlamp design customers. And so in headlamp design and thermal analysis, it's very crucial to be able to understand the distribution of heat loads in a headlamp, because that fundamentally changes the design itself, because you want the components in your headlamp to be robust and to be able to live the lifetime of the product without failing. And simulations historically have taken on the order of many days in some cases. So the challenge that we posed to ourselves in order to best support our customers was, how can we fundamentally change the timescales associated with thermal simulations with radiation to best help our customers cut down the time in their design cycles to produce a product and get it to market quicker. So we'll step back a little bit and talk about the very basics of heat transfer. There's sort of three categories that you can think of. One is conduction. So if you have a metal bar, for instance, where the left half is of a temperature T1 and the right half is of temperature T2, if you wait long enough, it will equilibrate. The whole thing will be an average temperature, and you'll have heat flowing from the hotter side to the cooler side, and that's what we refer to as conduction. You can think of convection as you get your hot cup of coffee, it's sitting on a desk, and it's convecting heat to its external environment, so it would cool down. It's warming up the air around it. And the other one, which is somehow perhaps a little bit less tangible but equally omnipresent, is thermal radiation, where whether that's you standing out in the sun or whether that's the light of a headlamp heating up its internal components. It's essentially electromagnetic radiation propagating through some media or sets of media and thus distributing heat along the way. It's a little bit more complex than that, of course, because the source of this thermal radiation is not necessarily just, a single beam of light that's shining. It could be diffuse, it could be collimated, and then consequently how that propagates through the system. So how the heat is distributed in a very complex system such as a headlamp, there's many ways that this can happen. So you can have diffuse reflections, specular reflections, and on and on. And so the kind of constituent components here for thermal radiative heat transfer are this, but modeling this computationally can turn out to be a very expensive endeavor, and it is often a very large bottleneck in thermal analysis, not just in headlamps, but in other applications, whether it's space systems, thermal or otherwise. So the two sort of key approaches that are used in SimCenter 3D thermal flow are either using direct view factor calculations, and one can think of a view factor as the kind of which part of a model can see what other part of a model. So if you have a headlamp, for instance, the main light in the headlamp can see a fraction of the model, but then you have propagation of the heat or the electromagnetic radiation through the model, and thus distributes heat in the headlamp itself. So the view factor calculation is kind of a simpler version of being able to calculate how heat is distributed in the system. And it's done with a single forward hit ray tracing type of methodology, where light is emitted from a source. You trace it forward and figure out which fraction of a surface can see something that's emitting, and then you distribute the heat loads using other types of methods. There's also Monte Carlo ray tracing, which is really classical type ray tracing, where you have light being emitted. It would bounce through the scene in the system and distribute heat along the way. And so we support both of these methods in the GPU accelerated framework that I'll talk about. And they both have their pluses and minuses and their applications in either headlamp analysis or other types of thermal analysis. So as I mentioned, the radiative heat transfer with high fidelity is a very computationally costly endeavor. It often is the lion's share of the work when you're doing thermal analysis with radiation. We have existing CPU implementations. However, we're aiming, or we have at least partially replaced both of these methodologies with a GPU implementation. And the reason we're doing this is that we want to change the expectations of our customers. We want to have something that is fast, that is, as robust as we can make it, and giving our customers the best bang for their buck. So what we've done is implemented a new GPU-based technology which supports direct view factor calculations and robust Monte Carlo ray tracing. It requires an NVIDIA GPU, and we've actually partnered with NVIDIA and had a presentation at the NVIDIA GTC this year. It's massively parallel. We have huge performance gains. It's library based, and this technology could be applied in other products or workflows. And if you're curious about that, feel free to reach out to me after the presentation, and I can put you in touch with the right people if you're additionally curious about what we've been doing. So to give you a flavor of what it is that we've achieved with this new GPU technology, we've taken a sort of in-house test model, which was actually a headlamp, but not a customer-facing test model. And historically, what we've seen with the CPU implementations is that it's taken a very long time to do these calculations. In our current implementations, with 10 CPUs, it takes on the order of 75,000 seconds. With 40 CPUs, so it's MPI parallelism, it's taking on the order of 22,000 seconds. However, with our new implementation, which is a single commodity level desktop GPU, we can do the same simulation on a single PC in less, on the order of time that it takes to go get a cup of coffee. And when we were initially developing this, that was the kind of ethos that I was trying to bring to the team, that if we can have something that brings the cup of coffee factor to our customers, where they start their thermal analysis, they can go away with their colleagues and come back and their thermal radiation calculations are done, we will have succeeded in what we're doing. Of course, implicit in all of this is robustness and fidelity of results, which also comes as part of this product. So right now, with these types of things, that's exactly what we've aimed to do. We've made this fast enough that we've changed the game for expectations for thermal contribution, radiative heat calculations in thermal analysis. Of course, I'm giving you a very biased opinion because this was something that I had worked on directly with the team at Maya, but I'd like to hand the ball over now to Robert Herpy and Harold McFarland, who give you their perspective, the customer-facing perspective, and how they've taken these changes and implemented into their workflows in thermal analysis for headlamp design cycles.
Thank you, Martin. That was a great explanation on heat transfer and how Maya has implemented these GPU solvers for the increased simulation speeds when compared to those traditional CPU methods. So yeah, my name's Robert Herpy. I'm a senior engineer, assistant manager here with Stanley Electric Design Group, and I've been working closely with Harold McFarland, who is our CAE senior engineer. He's got over 15 years of simulation experience and more than 30 in the automotive lighting field. So it was great to collaborate with Maya on this activity to kind of show what the real world example was. So just a quick background on Stanley Electric. We're a global company, and out of London, Ohio here, we're primarily focused on automotive exterior lighting and design and manufacturing. So we're doing headlamps, tail lamps, fog lamps, any lamp that goes on the exterior of the vehicle. That is what we are focused on here. So thermal simulations are very important for our lighting development so that we ensure we're choosing the appropriate materials and that those devices are able to stand up to the harsh environments that vehicles are seeing. So today we want to try to explain the computational power that was needed to run some of these larger models and how that has affected our workflow in a positive way. So some of the things we'll use thermal analysis for are, like I said, to confirm different materials, maybe different layouts, electronic components, and then, even simulating different engine room temperatures or external vehicle temperatures, whether it's cold weather or hot weather, different humidities, so on and so forth. So in the automotive industry, it's very common. You're able now to purchase a lot of different trim levels when you go to the dealership. Sometimes these different trims come with different lighting packages, and each of those lamps might perform in a different series of ways. So this was a couple test conditions that might be common for a headlamp. The left one shows an LED turn signal from a light pipe and the low beam lit there in the center, while the condition on the right shows just DRL function lit. Now, each model has a ton of different surface treatments, from those diffuse to specular reflective surfaces that Martin was mentioning earlier. And those are also sometimes variables in lamps. You might have one that's painted black versus one that's metallized and shiny. So with all these different trim options that are available in the different lighting scenarios, it's very possible and not uncommon to eventually see double-digit options and lighting scenarios that we would have to simulate. So that can become a very big problem very quickly with these large models and if solve times are very slow. So traditional simulation methods required many CPUs to get that computational power we needed to solve these larger headlamp models. One typical setup could be one host machine, parallel processing to 3 servers with maybe 8 CPUs each, which could take up to 3 to 8 hours to solve the model depending on the complexity. And then another typical setup for larger models like a headlamp could be that single host machine paralleling to up to 6 servers or more, with solve times anywhere from 6 to 30 hours. So any number of servers could be added, but the run times could still be long and potentially taking up to a day to solve. So you can see how this can add up quickly if you're doing multiple variations. So now consider if you're only using a single machine to solve that model. It might take up to, for one of the small models, up to 24 hours to solve just one of those test conditions. But through that parallel processing to the server, we were able to reduce that down to a reasonable amount of time, to about 5 hours, or almost 5 times faster. So adding additional computers was kind of the traditional method to increase speed through these CPU methods. However, that was always kind of weighing on budgets to add machines and maintain existing devices, which was always costly and required additional space and infrastructure here in the office, and planning to make sure that those were available. So to compare GPU to CPU, our process was to create kind of a simple headlamp model that included some LED light sources and halogen sources to cover kind of all the aspects of heat transfer that Martin previously explained. This model had about 135,000 elements. And you can see it there on the left, kind of a fun, unique looking thing that we created, and the final mesh model there on the right. So in the earlier CPU simulations, higher element quantities seem to always increase the run times. So it wouldn't be uncommon for some early simulations to maybe increase mesh size to reduce the elements. And when you increase those mesh sizes, you tend to lose geometrical accuracy of the surfaces that you're evaluating. So you might be sacrificing a little bit of accuracy for quicker solve times. You know, with the advancement of headlamps today and lighting, there's smaller features, there's more components. So it's very critical to make sure our accurate shapes are included in the model to make sure that those ray traces and radiation are accurate. So this GPU has basically enabled us to maintain those finer mesh sizes while continuing with good accuracy without sacrificing that computational time. Additionally, something to mention with the CPU solver method, if you consider a department that might only have 2 of these licenses, you would possibly need to split your resources to have them both functional, similar to the small model method on the left, where each host machine had 3 servers doing it. But if you needed to run a larger headlight model with a lot of elements, you may need to pull all of your available resources under the one host, basically rendering your second license useless because you wouldn't be able to solve a model in a reasonable amount of time. So it kind of just goes unused, which is money just sitting there. So now comes the GPU solver. So when considering that one CPU machine with the model, you would see maybe a solve time in about the 24 hours. And then through the parallel processing with CPUs, you might be able to decrease that by under 6 hours. But using the GPU, we were able to realize an improvement of up to 12 times, even on the simple model. And we expect even better improvement with more complicated models with even more elements. So this was big for us. Additionally, regarding the GPU solve, this allows us to free up those additional resources because we're no longer needing to parallel process to those servers for the larger models, which means we can run more test conditions concurrently, increasing productivity and reducing those costly maintenance and budget plans for those servers. So overall, our results showed that through this CPU method, when you consider 4 computers, it might take up to 5 hours to complete one of these test conditions. But with the GPU, we were able to complete both of those test conditions with a single machine in much less time. So this has greatly improved our workflow, allowing us to perform more iterations of the early designs to ensure all lighting conditions are evaluated and optimized. With our advancement of exterior lighting and additional functionality these days, it's critical to understand those inner workings and thermal limitations of the design in every different environment that could be possible, while still meeting the fast schedules of that automotive industry. So using the GPU has allowed us to really speed up that process to understand earlier where we may need to make changes before it becomes a costly change. So in conclusion, for us, we were able to double our output in regards to solve time when considering a single license, and realize up to almost 4 times the output due to the optimal license usage, since we're able to use them concurrently. We were also able to transfer our computing power resources to other areas of need in the department, which saves future capital investments and expensive maintenance costs. So GPU is the new standard for us to parallel solve for the view factors for all of our thermal simulations. And it truly is impressive how much quicker GPU can be. So I'd like to kindly thank you, Martin and Harold, for your work and collaboration. And thank you all for listening and taking time today to join this presentation.
I'd like to echo that as well. I'd like to thank Robert and Harold for all of their time and collaboration on this. And I really appreciate it professionally and personally. So thank you. If anyone would like to follow up with myself or Robert or Harold directly, there's our contact information and the websites for Maya and Stanley Electric. And there's a little QR code there for something that's coming out from Maya in the recent days, if people are interested. So thank you, everybody, and enjoy the rest of your day.